Okay, hello. Welcome to lesson 12.3 on explicit and recursive formulas and a little bit more. We're also going to talk about quadratic sequences as well. Let's talk about it. There's actually not a lot of emphasis on recursive here, I guess, but it's just introducing the idea. You'll get a better understanding of if you work with them, on the homework or whatever. So here we go. So our warm-up in class is to just kind of recall what we were doing in the last lesson and find the sequence, right? Determine the 5th, 6th, and 7th term of the sequence and blah, blah, blah. So I'll go ahead and do that real quick. Remember, last time we talked about arithmetic versus geometric. So 9 to 4 and 4 to -1 and -1 to -6. You're just looking for, what's the pattern here, right? Looks like it's -5 every single time. I mean, we can try multiplying, but it seems, pretty evident that it's subtracting 5 every time. If I have the first 4 terms, so I want to find the 5th, 6th, and 7th terms. So -6 minus 5 would be -11. And then -5 would be -16, and then -21. Right? Yeah, and that's just subtracting 5 every time. So that's pretty quick. The more challenging part is determining the 50th term because, well, you're not going to do that 50 times, are you? I hope not. Sorry for the yawn. It's 11:20 p.m. on a Tuesday. But I want to figure out the 50th term. So in order to do that, I need to find an explicit sequence, right? It's an explicit formula that'll tell me what a sub n is. Well, last time we talked about that for any arithmetic sequence, you can see, notice, right? This sequence is arithmetic. So, we said last time that a sub n can be found by doing the first term a sub 1 plus n minus 1 times d, where d is the common difference. And this works for any arithmetic sequence. So we say a sub n is the first term, which is 9, plus n minus 1 times d, and d is, in this case, -5. So I suppose I could clean that up a little bit if we'd like. I'd say a sub n equals, I'll distribute the -5 so that it's 9 plus -5n plus 5. That's just distributing that -5. And this is yielding me -5n. 9 plus 5 is 14, like so. Okay? And so I just want to find the 50th term. So I will do, right, a sub 50 equals -5 times 50 plus 14. And I should get that a sub 50 equals -236. Yeah, that makes sense. I think so. Cool. And that's just the warm-up, so yeah. Okay, so let's get into the lesson. Definitions. So what is an explicit, what is a recursive? We actually looked at that word explicit last time. We just didn't explicitly say what it was. So an explicit formula for sequences relates each term in a sequence directly to its placement in the sequence. So basically, it's what we just wrote here. This thing. That is an explicit formula because what it does is I can find any nth term, right? Any value of n can be found by placing the value into the formula. So if I wanted to know the 50th term, I just plug in 50 and it tells me what it is. That's what an explicit formula is, right? So if you wanted to know the 10th, you substitute n equals 10. So finding this rule, right? Finding the formula, where you can plug in anything, that's explicit. But this other word we're introducing is called recursive. So what is a recursive formula, right? Well, it says a recursive formula always uses the preceding term to define the next term in the sequence. So if you look back, right, it's similar to how you did the beginning, right? How did I know it was negative 11 and negative 16 and negative 21? Well, I didn't come up with the formula, right? I just thought, well, I noticed that the common difference is negative 5, and since I know that the fourth term, right, the fourth term is negative 6, then I know that the fifth term is negative 11. And because I know the fifth term is negative 11, I know that the sixth term is negative 16. So as long as I know the previous term, I can determine the next one. If I have this term, I can determine the next one. And so this is what a recursive formula does. If you wanted to know, say, the 10th term, you would have to know the 9th term first. If you didn't know the 9th term, you couldn't do this. And so when you found the next three terms, so that warm-up example, that's a recursive method, okay? This formula will only give you the very next term, so it's not a generalized, I can find any term I want. It really only tells you the next term, and only if you already know the previous term. So for a recursive, you always need two things, right? To write a recursive formula, you need to show the relationship between a sub n, which is your sequence, right, and the previous term. And so what is the previous term, right? Well, think about it like this. A sub 1, A sub 2, A sub 3. These are my sequence, right? The next term would be A sub 4. Okay, so A sub 4, what's the previous term? It's A sub 3. And what's the previous term of A sub 3? It's A sub 2. You say, okay, I got that, Mr. Spake, duh. I said, well, what's the previous term to A sub n? Well, what are you doing, right? If you're going backwards, 4 to 3 and then 3 to 2, the previous term, if I don't know the number, I take that number in and I subtract 1. So A sub n minus 1 is actually, that refers to the term before A sub n. It doesn't mean, like A sub n and then like a minus 1 or, A times n minus 1 or something like that. N minus 1 is the index telling you it's the term prior to n. So you need that relationship, whatever that is, right? And it doesn't have to be arithmetic. It could be geometric. It could be something else, right? And then you need to have the initial. You need the initial term, A sub 1, or some, I don't know, some particular term. Oh my gosh, I can't write. Some particular term. Meaning you have to know at least one value, okay? Usually you need to know the first one because that's how we start them off. But, you could reference it off others and then try to backwards engineer stuff, but whatever. So let's look at an example. So the sequence A sub n is given by the recursive formula below. So we have two things here, right? You have the relationship between A sub n, the current term, and A sub n minus 1, the previous term, right? So what does it say, right? What does this say? This line tells you that the term, or I should say, the current term, right? The current term is 7 less than the previous term. Does that make sense? Because what you're doing, right, you're saying A sub n is equal to, right, that's the current, right? That's A sub n. the previous is a sub n minus 1. And what am I doing to the previous? I'm subtracting 7. So I take the previous number, I minus 7. That gives me the current term. Okay? So if you want to say, the current term, that's a sub n, is 7 less than the previous term, that's a sub n minus 1. Okay. And then what does a sub 1 equal 18 mean? That means the first term is 18. That is what that means. Okay, so let's write an explicit formula. So that way I can find any term in the sequence, right? Okay. So if a sub 1 is 18, maybe let's make a table, yeah? Here's n. Whoa, what is that shape? Try that again. There's n. Boop. I like to draw the straight lines. And then this is a sub n. So the first term is 18. So what is the second term? Well, the current term, as if I am reading this, right? The current term is 7 less than the previous term. So this next term is 7 less than 18. So that's going to be 11. If I go to the next one, then 3, right? 7 less than that. 11 minus 7, that would get me 4. I could keep going, right? The fourth term, 7 less, I'll get negative 3. And I mean, I can do that, but it's not necessary to find all these terms. It's just I'm showing you how the recursive generates the sequence, right? This helps generate the sequence. So it is in part, it's a way that defines the sequence. So we want to write an explicit formula so that way we can find the 40th term because Lord knows I'm not doing 5, 6, 7, blah, blah, blah to 40, right? We got to figure out what's going on. Well, what's happening here? Because this is minus 7, minus 7, minus 7, this is a common difference, right? Common difference where d equals negative 7. So this is an arithmetic sequence, just like the warm-up. So since it's an arithmetic sequence, we know that a sub n equals, and we did this last time, remember, a sub 1 plus n minus 1 times d. So then and this gives us the explicit formula. So the first term we said was 18 plus n minus 1 times d, where d is negative 7. And, I can distribute that, right? It's 18 minus 7n plus 7. So this tells me, right, therefore, a sub n equals negative 7n. 18 plus 7 is plus 25. Yeah. There it is. Okay? Cool. And so now I want to find a sub 40. So that's negative 7 times n, which is 40, and then plus 25. So that should be like negative 280 plus 25, which I think comes out to negative 255. Always double check my calculations. You never know if Mr. Spake makes a mistake in a video. He is human after all. That can always happen. Okay, so that's good. Okay, we'll do another example. The next one I would probably just leave for you guys to do in class, but I mean, hey, it's the video, so I'll do it too. I do encourage you to pause and try it, though. Yeah. So the sequence a sub n is given by the recursive formula below, blah, blah, blah. So I'll probably write this again, just to really hone in on what the heck this all says, right? The current term is found by multiplying the previous term by 2/3. I mean, that's what that says, right? It's 2/3. Because the current term is the previous term times 2/3. Yeah? I didn't know that that was... Is that a square? It's supposed to be round. Oh, interesting. Maybe I've been using the wrong operator when I type these things. I'm going to have to look into that. It's not supposed to be square. Sorry, I'm thinking out loud. Current term is found, blah, blah, blah. Yeah. And then, of course, this says, right, the first term is 243. And so, you know, if you wanted to make like a table or whatever, you know, you could. I don't think I want to, though. I guess I will. I'll say n, and I'll say a sub n, but I'm going to do like only 3 of them. So first term is 243. Second term, 243. Do I have my phone on me? I need to actually pull out a calculator. I don't want to do this. I think it's 81 times 2, so it should be 192. Is that right? Let's do this. 243 times 2 over 3. What? 243 divided by 3 times 2. Oh, 162. Okay, what the heck was I thinking? 162. Glad I grabbed a calculator. 3, and then I say divided by 3 times 2. I'll get 108. And look, you can keep going, but it has a common ratio, 2/3. We don't actually need to write out this table, okay? We don't. It's not necessary. Again, I'm just modeling to show you how the recursive formula defines the sequence, and I can generate the numbers from the recursive formula. But if I just want to find the explicit formula, well, if you go back to lesson 12.2, which I conveniently have here, we ended the lesson with this piece right here. The nth term of a geometric sequence can be found by taking the first term and multiplying by the common ratio raised to the n minus 1 power. You can just use that fact here, okay? You don't have to, like, reinvent the wheel here. I mean, you're welcome to, but a geometric series, I might say this, right? Common ratio r equals 2/3. So put a little asterisk. This is a geometric sequence. So a sub n equals the first term a sub 1 times r to the n minus 1. And this is just the general formula for blah, 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 geometric. So then a sub n equals the first term, 243, times r, which is 2/3 to the n minus 1. And that is the sequence. I can box that. It was a terrible box. Let's try that one more time. Boom. Okay. Oh, I don't like that. I'm going to erase this. And I'm going to write n minus 1. Oh, still too stubby. Okay. Here we go. And now what? 12th term? Yeah, no problem. No problem, Chief. A sub 12 equals 243 times 2/3 to the 12 minus 1. And I'm not doing that by hand. I sure hope you're not. I mean, you can. I have no idea what that is. Let's look at my notes. I already calculated this. This is 2.809. 2.809. And that is rounded to 3 decimals because it is much more than that. And yeah, good enough. Okay? Yippee! Woo! Okay, let's move on. Okay. other methods for explicit formulas. So, we found the arithmetic sequence, blah, 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 with the, the formula, right? But, there are other ways. Interesting things. And we're about to make an interesting connection here. If you didn't realize this in Algebra 1, it's fine. Maybe your teacher did it, maybe they didn't. But I'm going to show you something here about arithmetic and geometric sequences. So recall that the explicit formula is this. So the goal is find the explicit formula for this arithmetic sequence. Yeah? Well, look, 3 plus 4 is 7. 7 plus 4 is 11 plus 4. Yeah? So a sub n equals a1 plus n minus 1 times d, where since I'm at the common difference is d, right? So d equals 4, and a sub 1 is the initial term, 3. So then a sub n is 3 plus n minus 1 times d, which is 4. Yeah? And yeah, I mean, you can distribute this, right? I could go ahead and do that. Or I can just leave it like that. Maybe I'll just leave it like this. You don't have to distribute it, really. I mean, n minus 1, you can calculate that. It's not bad. Okay. But what I want to do now, sorry for yawning, is look at the sequence in a bit of a different way. Because we said that these things are functions, right? Well, if I just handed you this table, and rather than saying it's S and S, these are S's, aren't they? I got so used to calling them A's. S sub n, S sub 1, S sub n. This is S. Just because this example used S instead of A. So it's no big deal. So this is like your X, and this is like your Y. Well, you still notice that it's plus 4, plus 4, plus 4. And what's happening between your ends? They're plus 1, plus 1, plus 1. So if you think about your parent functions, I mean, what kind of function is this? How is it changing? Well, it's adding 4 every time, and every time that increment is 1 in the x value. So for every y value that goes up by 4, x goes up 1. And it stays like that. It doesn't change, which means it has a constant rate. It has a constant rate of change. Constant rate of change. Now, which function do we know has a constant rate of change? Linear, right? Linear lines have a constant rate of change. The slope doesn't change. It stays the same up and down, like so. So, actually, this arithmetic sequence is a linear function. And if you think about it, right, this rate of change, the slope, which is m, right, is rise over run, or also known as the change in y divided by the change in x. And if you look at my y values, which are, this row is like x and this row is like y, then the y values are changing by 4 every time while the x values are changing by 1. So that means I have a slope of 4. And if you think about the y-intercept, well, the y-intercept happens, when x is 0, right? So if x is 0 here, then what is the y value here? Well, it's 0 is 1 less than 1, so I just got to go back a term, right? 0 plus 1 gets me 1. So I ask myself, what number plus the common difference, 4, is 3? It'd be negative 1. So actually, that's where my y-intercept is. It's at 0, negative 1. Now, because you have the slope and you have the y-intercept, then by slope-intercept form, which we should know, right? Slope-intercept form, that's y equals mx plus b. You should know that the sequence S sub n is the slope 4 times your variable n, which right is x, but it's supposed to be n because it's a sequence, plus, or rather minus, because it's plus negative 1, so it's minus 1. And that is your sequence. Now, compare this formula to what we got way up here. Are these the same thing? Well, I put a star. Notice S sub n equals 3 plus n minus 1 times 4, right? If I zoom in on this, let's distribute that 4. That's 3 plus 4n minus 4. That's 4n minus 1. Hey ho howdy. Those two things are the same. Same thing. Same equation. Okay. So, for an arithmetic sequence, you know, you could just view it through the lens as a linear function, because that's kind of what it is. It's just a linear function. Common difference, slope. The slope is the common difference. And the y-intercept is when x is 0, so it's, you think of it like a sub 0, right? I know we start these things on the first term, but, you know, all you have to do is go back 1, and that's the y-intercept. So you could use y equals mx plus b for some of these arithmetic sequences. So that's just a connection. Let's talk about geometric sequences now. So recall the explicit formula for a geometric sequence given by this, right? So let's find the explicit formula here, right, for these numbers. Well, S sub n equals S sub 1, the initial term, times r to the n minus 1, where the first term, S sub 1, looks like that's 12. What's the common ratio? Well, I think 12 times 3 is 36. Seems like 36 times 3 is 108. Yeah, 108 times 3 is definitely 324. So it looks like the common ratio is 3. So I could plug these things in here, right? That means S sub n equals S sub 1 is 12 times 3 to the n minus 1. And I mean, that's it, really. Done. That's the explicit formula. Easy. So now let's observe the table below. Well, I know I have a common ratio. I'm doing 12 times 3 times 3 times 3. What parent function does that? I want you to think about that. If you need to pause the video, give yourself a second. Which of your parent functions? Well, think about what's happening to these numbers, right? If I want to plot these on a graph, 1, 12, maybe I say that's there. 1, 36, that's 3 times as tall as that. But 108 is 9 times as tall as the 12, so it's kind of like up here. And 324 is 27 times as tall. Which function does that? Which function looks like this? Hopefully you said exponential. Yeah? So this is growing exponentially. If you just look at the table, right? Our growth factor, this is with a growth factor, b equals 3, if you recall finding the growth factor. So yeah, we put it down here in words. This is actually an exponential function with a common ratio of 3. Common ratio of 3. And notice that language is actually shared here with geometric sequence. If you think about the y-intercept, right? The y-intercept is when n is 0. So what number, right? What number goes here? What would you multiply by 3 to get 12? You would say 4. So I know that the y-intercept, yikes, sorry for scrambling all over the place. The y-intercept is at 0, 4. I really should write this on a flat surface and not on my couch, but that's okay. It's more comfy here. Y-intercept is 0, 4. Now here's the thing. By general exponential form, by the general form, which says y equals a times b to the x, well, a is the initial value, right? Or also known as the y-intercept. And b is called the growth factor, which is the thing you're multiplying by every single time. Well, we know those things, right? So S sub n equals a, the initial value, which starts at 4, because that's the y-intercept of the function, right? 4 times the base is 3 to the x, or in this case, n. And so that is my sequence. You might say, okay, well, I compare this to my previous one. They don't look the same, but compare this to S sub n equals 12 times 3 to the n minus 1. For some of you, it's very obvious. For others, I want you to pause and think about this. Are these the same thing? And if they are, how can you find it? Take a moment and see if you can prove that. Are these two sequences the same? Answer yes. And if you don't want the answer spoiled, go ahead, pause, and think about it. Well, remember when we talked about exponential rules, which was actually rather recent in our class? 3 to the n minus 1, that's 3 to the n times 3 to the negative 1. And hey, what's 3 to the negative 1? What is that? Here, you know what? I'm going to lasso this real quick. I ran out of space here. I need more vertical space here. Yeah. I'm sorry. Hold on. I'm ruining the suspense because of mere edits. Compare this to S sub n equals 12 times. You probably say, oh, Mr. Speg, I already figured it out. You don't even need to write it. I say, I know, I'm sorry. I spoiled it, and then I didn't prepare. Times 3 to the negative 1. Well, what is 3 to the negative 1? That's what I was asking, right? 3 to the negative 1, we know, is 1 over 3. What's 12 times 1/3? 4. Boop. Same. It's the same thing. Boom. Yeah. So if you manipulate the exponents and blah, 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 you should see these are the same formula. It's just they're kind of telling two different stories. This is telling you the story about the sequence of numbers starting at 12. This function tells you it's an exponential function that actually starts at 4, it has a y-intercept of 4, and then grows. So they grow the same way, and they really are the same sequence of numbers. But in particular, this sequence, S sub n, does start on 12. And it is, we call it discrete because it's not continuous. It only takes integer values for n. There's no a sub 1.2 or a sub 2/3, right? I'm not considering fraction or decimal indices, meaning an plural of index. So that would be why. So anyway, they're different, but they're the same, if that makes sense. Okay. All right. Last piece of the video deals with quadratic sequences. I do think the video is starting to get a little bit long, but hey, whatever. I mean, when we enjoy math, we love it, right? We're having a good time. I'm having a good time, at least. So what if it's midnight on a Tuesday night and there's a STAR test tomorrow? So what? Who cares? Here we go. Given the sequence t sub n equals 5, 6, blah, 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 find t sub 8. Okay. Now, this is one I really want you to pause the video and try on your own because it doesn't follow the patterns you've done yet. So I highly encourage you to pause and really try this one, okay? I am going to go through it, however. So what I'm going to do here is I'm going to make a table for the sequence t sub n. So I've got one, n is the index, and the sequence, come on, straight line, is t sub n. And it's 1 gives me 5, 2 gives me 6, 3 gives me 11, 4 gives me 20, 5 gives me 33. And so I might ask myself, can I predict 6, 7, and 8? I don't necessarily need to find a explicit formula. I mean, I suppose we could, but I only need to go the next 3 numbers. I think I could manage that if I can figure out what the pattern is, right? So the first thing we might do is look at the common difference, right? It doesn't really look like I'm multiplying by anything because, like, 5 times what gets you 6? Well, it'd be 5 times 6/5. That's what would get you 6. And you might ask, okay, well, so is 6 times 6/5 11? No. So multiplication, I don't think that's really related here. And maybe addition isn't either, but let's really look at it. Let's write it out. So to get from 5 to 6, that looks like +1. And to get from 6 to 11, that looks like +5. You get from 11 to 20, that looks like +9. And to get from 20 to 33, that looks like +13. Okay. And I look at this and I say, do they have a common difference? No. So is this an arithmetic sequence? No, because it's not linear, right? However, take a look at the common differences. Notice this has itself created its own sequence. You're now looking at a sort of subsequence, if you will. Maybe that's not actually the right word, though, because it's not within this one. But whatever. It's another sequence. 1, 5, 9, 13. And if you look at those numbers, perhaps you notice something there. Because to get from 1 to 5, you do +4. And to get from 5 to 9, you do +4. And to get from 9 to 13 is also +4. So, okay. Can I work with that, right? Right? This is saying, so this is +4. This is also +4. And this is also +4. So this pattern I found, it's not a common difference, but it is a common second difference because I've done the second difference. And so now I ask myself, well, how can I find the rest of these terms? Well, I know that from 13, I need to know what I need to add here, right? I need to do 33 plus something gets me this number. So what is that something? Well, I need to do 13 plus 4. I find that that is 17. And so now I do 17 plus 33. I get 50. And then I repeat this pattern. I need to do a plus 4 in order to figure out what I need to add to 50, which is going to be plus 21. So that should be 71. And then I'll do it one more time, plus 4, which means I need to add 25 to 71, which looks like that's going to be 96. So T sub 8 equals 96. So we found it. Beautiful. Isn't that just lovely? Isn't that just great? I think that's awesome. So we found a pattern from the common differences. Now, it kind of spoils it because it's in the subtitle, quadratic sequences. So yes, it does spoil it. But if a sequence has what's known as a second common difference, this is the plus 4s, then that means it's quadratic. And you may have learned this in Algebra 1. If you have a second common difference, it's a quadratic function. To find the explicit formula, well, believe it or not, you've actually already done this before. This actually isn't new. To find an explicit formula, you're going to want 3 terms of the sequence, and you're going to use these 3 terms to create a system of equations. Oh, yeah. Oh, good old Unit 3. Oh, remember Gaussian elimination? Use the standard form equation for quadratics. Now, that's the standard form equation for a quadratic function, but we're not talking about a function. We're talking about a sequence, and we're talking about T sub n. So we're going to use T sub n is a times n squared plus b times n plus c. Basically the same thing, but a little bit different. So suppose I want to find the explicit formula for this sequence. Well, remember in unit, was it 4 or 5, we were able to find, if you're going to use a system of equations, right, you have 3 unknowns, A, B, and C. So because you have 3 unknowns, you need 3 equations, right? 3 equations, 3 unknowns. How do I find these? Well, in the previous context, we said this makes a parabola. You need to find 3 points on the parabola because every point is x comma y, right? And then you can plug those x comma y's in and figure out, what a, b, and c are using systems of equations. In this case, we're not really talking about the parabola, we're talking about the sequence. But you can use the exact same idea because I'm going to make a little table here. We already have this table from above, but I'm just going to isolate it here. Okay? Boop, 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 like so. N is 1, 2, and 3 because I need 3. And this is 5, 6, and 11. Well, if T sub n equals a n squared plus b n plus c, then what is T sub 1? Well, T sub 1 equals 5. But that 5 equals, if you plug in n, it's a times n squared. So that's a times 1 plus b times 1 plus c, which I'm just going to simplify that a little bit. It's not really simplifying, but just, make it a little bit cleaner. It's just a plus b plus c. T sub 2 is the second term, which equals 6. But if I plug in here, 2 squared is 4, so this is 4a plus 2b plus c, and now the third term, which is 11, which equals 3 squared is 9a plus 3b plus c. And now that you have a system of three equations, guess what you can do? Matrix. The matrix. Yes, they've returned 1, 1, 1, 5, 4, 2, 1, 6, 9, 3, 1, 11. Boom. And now that I've made this matrix, I say row reduced echelon form. Remember this? Oh my gosh. Full circle, right, guys? Oh my Lord. It's like everything we learned this year comes back together in one nice, neat thing. And so I already ran the calculations. I get 2, -5, and 8. I figured this video is going to be long enough. You don't need to see me typing in the matrix into a calculator, right? And so this tells me A equals 2, B equals -5, and C equals 8. So therefore, the sequence T sub n is defined by 2n squared minus 5n plus 8. And now I can use this to find any term in this quadratic sequence. Now that's pretty beautiful. And notice we're talking about a sequence. Yeah, it's a parabola, but we're not really talking about the function. We're talking about a quadratic sequence of numbers. But methods of old still are useful, which is kind of neat. So, seeing this, you should be able to get example 2 here. I'm going to go ahead and do it in the video just to be sure, in case you're absent or whatever. But I am leaving this for the in-class practice to figure out what this sequence is. And you might find something surprising here if you look really, really carefully. So here we go. We need to find, we're given the recursive formula, we need to find the explicit. Now, if we're going to use the same idea, we need 3 terms. I have T sub 1, right? If this is n and this is T sub n, T sub 1 is 4. But what is T sub 2? Well, T sub 2 is the previous term, T sub n minus 1. That's T sub 1 plus 2 times n equals 2 plus 1. But what is this? So it's T sub 1 is 4 plus 2 times 2 is 4 plus 1. That equals 9. So that's that term. And then I look at T sub 3, right? T sub 3 is T sub 2 plus 2 times n, and n is 3 plus 1. T sub 2 was 9, so this is 9 plus 6 plus 1. That is 15. So 3 is, hold on. I think I did that wrong. No, 16. 16. Now, something quick here. I'm going to go ahead and find one more. T sub 4, just to really solidify this. T sub 4, okay, actually, I'll find this in a second. What I want you to look at, 4, 9, 16. Is that a pattern? Is that a pattern? Well, I consider this for a second, right? 4, I'm going to put this in blue, is 2 squared. But if I relate that to 1, right, how do I get 1 to make it 2? Well, if I take the index 1 and I add 1 and I square it, I get 2 squared, which equals 4. If I take the index 2 and I add 1, I get 3. And if I square that, I get 9. If I take the index 3 and I add 1 and I square it, I get 4 squared, which equals 16. So the question is, can I repeat this pattern, right? Can I generalize this for a sub n? So is it true that if the index is n, can I do n plus 1 squared, right? Will this work? Well, let's see. If I do that, right, if I do 4, then 4 plus 1 squared is 5 squared is 25. True. Now let's use our recursive formula. T sub 4 equals the previous term, T sub 3, plus 2 times n, which is 4, plus 1. So this is, T sub 3 was 16 plus 2 times, that's 8 plus 1. So that's 16 plus 9, which is indeed 25. So it does look like I figured out the pattern. So I could say, therefore, a sub n equals n plus 1 squared. That will tell me any term in the sequence. Isn't that right? That's exactly right. But what about the whole matrices thing, Mr. Spake? I say, what about it? I said, did you really need it here? Maybe, maybe not. Because see, if you find the pattern, maybe you don't need to, right? So it's very free form. It's very, creative, and whatever you want to try, that will work. Now, if you want to do the matrix method, right, the matrix method looks like this. So a sub 1 was 4. And if you plug that into ABC, right, that's A plus B plus C because it's all ones. A sub 2 was 9, and that was going to be 4A plus 2B plus C. And A sub 3 was going to be 16, which was 9A plus 3B plus C. So that means you can make a matrix. 1, 1, 1, 4, 2, 1, 9, 3, 1, with 4, 9, and 16. And if you put this in row reduced echelon form using a calculator, you will find you get this matrix: 1, 0, 0, 0, 1, 0, 0, 0, 1. Where's my sheet? 1, 2, 1 is what I get. So 1, 2, 1. Which means A equals 1, B equals 2, and C equals 1. So therefore, it's not A sub n, right? Yeah, sorry. It's not A, Mr. Spake, it's T. Okay. I really gotta be consistent with that. Gotta really pay attention to that letter. T, T, T. Okay. Therefore, T sub n equals 1n squared plus 2n plus 1. And guess what? If you factor that, 1 and 2, what works? 1 and 1. T sub n equals n plus 1 times n plus 1. Therefore, T sub n equals n plus 1 squared. Oh my gosh! Whoa! Right? These two things are related. From here to here. Same thing. And that is just beautiful. I mean, come on. That is what math is about right there. It's not It's not just about getting the answer. It's about the interesting, different, creative approaches you can take to finding an answer. And the just awesome result that your answer can look like different forms and yet still be mathematically the same thing. It's just so beautiful. I mean, don't you think? Don't you think this is great? I mean, I think so. Oh, that's just a lovely problem right there. That's just really great. Okay. That ties everything together. I mean, that's so great. I'm sorry. I'm just relishing in the wonder of the beauty of this problem. It's just so great. So that is it for lesson 12.3. This one was definitely a long one. I feel like it's like an hour or so. No idea how I'm going to do this in class in time. Oh my gosh. Oh well. I guess we'll see what happens. Yeah. Okay. There we go. Hope you enjoyed the video. I know I had fun doing this one. So, yeah. Take care, and I'll see you around.